We'll start with number 1. So you have this function, capital F of x, and now capital F of x is defined as an integral of another function, little f. So this is little f. It's shown here geometrically. So now we're going to sort of test, can you take a picture and understand what's going on? And we're also going to test basic properties of integration. So here, where does the x show up? It shows up in the bounds. So we're just going to go through and work through every one of these and see what happens. So let's start with a. It's a very good place to start at the beginning. So take -2 and you plug it into your bounds. -2 squared is 4. A half of 4 is 2. And 2 minus 2 is 0. So it becomes 0. 3 halves times -2 is -3. And then f of t dt. Now this is sort of the wrong way to write the integral because we usually think of going from a to b where a is smaller than b. So the bounds are sort of in the wrong order. How do you fix the order? Yeah, you flip it and change the sign. So we're going to put a negative in front. Now we have the right order. So again, remember, orientation matters. We go left to right. So we come up to our picture and say, well, what does this mean? Well, it means we're going to go from -3 up to 0, and we're just going to the axis. So here, we're positive, so we're going down. If we were below the axis, we would go up to the axis. But we get this shape. And now, we're going to just use geometry. And geometry says what? Well, I see a triangle and a rectangle. And so the integral will be the area of the triangle combined with the area of the rectangle. In this case, the areas are positive because I'm above the axis. So negative area of the triangle is a half because it's half a box here. Area of the rectangle, 2 because it's 2 full boxes worth. So negative a half plus 2 are -5 halves. All right, so that's part A. Then we go to part B. F of -1. Well, that's the integral. When I plug in -1 squared is 1. So that's a half minus 2. So that's -3 halves. Plug in -1, -3 halves. F of t dt. So what do I get when I integrate from -3 halves to -3 halves? 0. So this is, if you ever see the bounds match, you're done. It's 0. All right. That one's not so bad. When is it going to get challenging? Well, don't worry. It'll pick up. F of 0. So f of 0. So that's the integral. Plug in 0. -2 to 0. F of t dt. Well, bounds are in the right order. So -2 to 0. So I'm back to just the rectangle. What's the area? And we're done with part C. So now we get to part D. So finally, aha, something interesting. F prime of 1. Well, if I'm going to compute f prime of 1, the first thing I should do is compute f prime of x. Just what is f prime of x in general? So I'm going to find that first. F prime of x. So I'm taking the derivative with respect to x of the integral. So what tool or theorem, think particularly fun theorems, do we have that let us take this derivative? The fundamental theorem of calculus. It sounded like someone said the dimensional theorem. No. Don't forget the fun. It always is the fundamental theorem. All right. So if I go from function to function, there's actually a nice generic rule that says, here's what you do. You say the function f, plug in the top, 3 halves x, times by the derivative of 3 halves x. That's 3 halves. Subtract the function f, but now put in the bottom, half x squared minus 2, times the derivative of the bottom, derivative of half x squared minus 2 is x. So that's f prime of x generically. So now we say, okay, what is f prime of 1? Well, according to this, f of 3 halves times 1 is f 3 halves times 3 halves minus f of 1/2 minus 2, negative 3/2 times 1. Well, come to the picture. If I go to 3/2, what is the value of the function at 3/2? It's 3/2. In fact, you can see it's on this line segment where y equals x. So this is 3/2 times 3/2. F of negative 3/2, what is that? It's 1. So minus 1 times 1. Or 9/4 minus 1, also known as 5/4. All right, and that's the first problem. Cool. So this tests on a couple of different ideas. So for instance, what did we test on? Knowing that we can interpret things geometrically. Knowing the fundamental theorem of calculus. Knowing that if you switch the bounds, it flips the sign. Knowing if the bounds agree, you get 0. So there's all sorts of good stuff in here. So even simple problems, lots of ideas flowing here underneath. Number 2. So find the integral from -1 to 9 of a crazy looking expression dx. What's the crazy looking expression? It's kind of, the thing that's hard about this problem is it's very intimidating. It's like, "Rah!" And it's like a new monster. It's like, wow, we've never seen this before. But the longer we stare, it's like, maybe it's not so bad. So what's happening is it says we're taking the max of 2 different parts. So the max of 2 minus absolute value of x minus 1, or 4 minus absolute value of x minus 5. So there's these 2 functions which involve absolute value of x, and then we're taking the largest one. So let's sort of get a handle on what these functions look like. So let's start with, if we just do one, the other one will have something similar. 2 absolute value of x minus 1. Now, to get a handle on it, it says start with something simple that you know, and just keep modifying it until you figure out what it's really doing. So really, this function seems at its heart to involve absolute value of x. So I'm going to start with absolute value of x. So here's absolute value of x. Now, let's think of things we can do. Well, let's go to our next step. Let's do absolute value of x minus 1. What does that do to our picture? Is that dark enough? Yeah, it's dark enough.
Moves it to the right?
Moves it. Now, this is the one that always throws people off because it's on the inside of the absolute value. If you're not sure, just think about where the tip of the absolute value will be. And the answer is it would be at when x equals 1. So it moves it over. To the right, to the right. When it's on the inside, you move to the right. Things like that, you know. Whatever it helps you remember. Okay. Then what happens? Well, let's think about the minus absolute value of x minus 1. What does that do? It flips. Negative just says flip it around the axis. Okay. And then finally, we get to the function 2 minus absolute value of x minus 1. So again, now we're here. What does the 2 have? What does it do? Shifts it up by how much? 2. It shifts it up by 2. So it does that. So what we see is if we think of this function here, and probably have a really poorly designed grid here, but if here's 1 and here's 2, it's like the absolute value function, but it's been moved up. So let's see, that'll be at 3. All right. So that's what the 2 minus absolute value of x minus 1 looks like. What is 4 minus absolute value of x minus 5? How does that behave? Well, it's similar. What's the difference? Where's the x value? So where's the tip, the top? At 5. And where's the y value? 4. So if I go up, it's here. And then I'm going to, again, go down. So if I'm at 4, it's going to cross through at 9. And if I go 4 across, it's going to cross through at 1. So those are my 2 absolute value functions. And I'm taking the lot max, which means I always take the one on the top. So I'm taking one on the top. So that's the function. It's these two peaks here. Now where are we going from? We're going from -1 to 9. -1 to 9. So our area is this. So that's what we're looking for. We can interpret it as the area underneath these pair of peaks. Well, cool. That's how we can interpret it. But then we have to find the area underneath these peaks. How does one go about finding that area? What can we do?
Find the area under both and subtract the triangle out. They're both crossing over the same place.
Yeah, there's lots of ways to do this. You can break this up into smaller shape, or you can think about combining things and subtracting things. So this is an interesting idea. If I find the area of both, so suppose I find the area underneath this smaller part. Well, how wide is the base? -1 to 4? Sorry, -1 to 3? 4. Height? 2. So the area? What? 4. Yeah. Another thing you can do is you can just sort of take the one half and flip it over, and you get a 2 by 2 square. So the area of sort of the smaller piece is 4. Now let's do the area of a bigger piece. So suppose I want the area of this piece here. So that one's a very large piece. So I'm going from +1 to 9, so that's 8. Height is 4. What's the area? 16. And then I have something that's so crowded you can't even tell what I'm drawing, but this little overlap. What's the base is 2, height is 1, so the overlap is 1. So 4 plus 16 minus 1 gives us 19. And we're done. That's not so bad. Man, why were we nervous about this test? Oh wait, there's some more questions. All right. Number 3. Rewrite the following as a single integral, some constant integral from some number to some number f of t dt, where a, b, and c are appropriate numbers. Ooh, boy, this is going to be interesting. Okay, so we have a whole bunch of integrals here. We're just going to go through one at a time and say what happens to each piece, and then we're going to put them together at the end. So for the first piece here, I want to get t on the inside. There's -x, so that's easy to fix. Just set t equal to -x. So dt would be minus dx. Or you could say plus dx is minus dt. So this becomes 2 is 2. Integral becomes f of t. Then I have dx. I'm going to end up with a minus sign somewhere. There's a minus sign. And then what are my bounds? Well, the old bound was from -2. Plug in -2. -2 makes +2. 1, plug in 1, get -1. So 2 to -1. Now going from 2 to -1, again, that's not quite the way we like to think about the bound. So what should we do? We should flip. But if we flip, what do we do? We change the sign. We have a negative sign already. So the great thing is we can get rid of the negative sign. So actually flipping sort of solves two problems at the same time. So we're going to get 2 integral -1 to 2. And I put dx there. I should have put dt. I'm so sorry. Double check. F of t dt. There we go. So that's the first integral. Well, you always got to start out a warm-up one. Okay. Now let's go to the next one. So the next one, what can we do? What's the right substitution? Well, I want f of t, so y to the 1/3. So what should dt be? 1/3 y to the minus 2/3 dy. Now, if you look, I have a y to the minus 2/3 dy, because that y to 2/3 downstairs is y to the minus 2/3, which is great. I don't have a 1/3, but I can do the following. I can move the 1/3 across. So 3 dt is y to the minus 2/3 dy. All right, so let's see what happens. So our integral becomes, we're going to have dy over y to the 2/3. That becomes 3 dt, f of y to the 1/3, f of t, this is all good. 8 to the 1/3 is 2, cubed root of 8. 64 to the 1/3, cubed root of 64, it's 4. All right, so those are the first two integrals. Okay, so now we go to the next one. Integral from -5 to 5, arctangent of z, f of z squared. Now, we might say, hey, what if we said t equals z squared? And then we're like, ooh, wait a second. We don't have a 2z on the outside. And we have this function, arctangent. Whoa, that's kind of odd. Why is that there? It's a very odd looking function. Is there anything we can do? Oh, it is an odd function, but not just odd in that it's strange. It's odd in that it has symmetry. So this function is odd. And what do I mean by odd? If you plugged in negative z, so again, when I talk about the function, ignore the integral, just the function. If I plugged in negative z, notice the inside here becomes square, so the negative goes away, so it doesn't matter what f is. You still get the same value. And arctangent is an odd function. Arctangent has symmetry. It's one of the reasons why arctangent is such a cool function. We're really fortunate that we got to learn so much about arctangent, but I want to assure you, as much as you know about arctangent this semester, you're going to know even more next semester. It's going to be great. Keep coming. Calc 2, the return of the arctangent. All right. So, because this is an odd function, I'm integrating from -5 to 5. What that means is any function which is odd, you get cancellation. And so this is 0 by symmetry. So this is sort of throwing it in the middle of like, hey, were you paying attention that you have things that you can use, ideas, to simplify things? It's nice to use ideas. We're definitely pro use ideas. Okay, that leaves us with one more to go. What's the substitution to make over here? 2 sine theta. And if you look, you'll see that dt is 2 cosine theta d theta. And that's perfect because we have a 2 cosine theta d theta. The 2 can come in. So let's see what we get. We're going to get f of t dt. And then we have to say, what are the bounds? What are the bounds? So let's plug in the top bound. We can do that first. Sine of pi halves is sine of pi halves is 1. Double makes 2. Sine of negative pi 6 well, sine of negative pi 6 is negative a half. But then you double that, you get negative 1. So it's integral from -1 to 2 of f of t dt. Okay, well, what can we do? Well, now at this stage, we just start putting things together. So for instance, we have these two integrals, same bounds. There's one of them here, there's 2 of them there. So if we combine these two, we'll get 3, integral of -1 to 2, f of t dt. Then I have 3, integral 2 to 4 of f of t dt. But we're not done because we have to get to a single integral. But now there's one more idea. See how I go end at 2 and I start at 2? It's like A to B, B to C. So what I can do is I can put those together into a single integral, 3, integral -1 to 4, f of t dt. And we're done. Because we got exactly what we wanted. So this tests on all sorts of things. Substitution, flipping the signs, moving things together, symmetry.
I don't know if it matters in this problem or not.
Right.
Why can we make
X and Y and Z and theta all the same thing?
Oh, why can we make X and Y and Z and theta all the same thing? This is a fantastic question because X and Y and Z and theta are just dummy variables.
Okay, I didn't know
They're
if
just,
it mattered.
they don't matter at all.
Okay.
You can use any symbol you want. If you wanted to, you could use emojis, but it's very hard because it's very hard to distinguish a smiley face emoji from a meh emoji from a frowny face emoji. On the other hand, the chocolate pudding emoji, apparently they called it a different thing, but it's very easy to identify that one. Oh yes, there's another question.
So how would that interaction work if, say, because both have are multiplied by 3.
Right.
How would that work if the second to 2 to 4 there was a 2 there instead of a 3?
Then we can put them together.
Okay. So those
Yep.
would have to be the same.
Yes. And so if we got to a point and they weren't matching up, we'd be like, let me go back and check.
Okay.
Because
So it should just kind of work out that way.
it's almost like, yeah, you should think like, they should have rigged it to work. And so if it's not working, it's like, I suspect there's an error.
Okay.
Now in real life, you're like, well, I don't know if they rigged it to work, because nature has nature is very finical. Finical? Is that a word? Finicky? Finicky sounds like a better word. So be very careful about nature. It messes with you. Just when you think it'll work. Okay, so this is a fun-looking one. A particle has acceleration a of t equals 4t plus 4 divided by t squared plus 2t plus 2, quantity squared, and at time 0 is located at position 0. As time goes to infinity, the particle moves. And it moves to a particular location. Doesn't blow off to infinity, doesn't blow off to negative infinity. It moves to one spot. And that's what we're told. So we're really told two pieces of information. We know where it's starting, and we know where it's going to end up if we let time go to infinity. So given those two pieces of information, we want to A, say what's the velocity of the particle at time 0, B, where does the particle move as time goes to infinity? Okay, it's one of these things that feels like we don't have enough information. Or do we? Well, we won't know until we answer the question. All right, so we're given acceleration. We need to talk about velocity and position. So how do I go from acceleration to velocity and position? I use integration, or I could use the phrase anti-differentiation if I wanted to use more vowels. All right, so let's start by finding velocity. Velocity, antiderivative of acceleration, or antiderivative is also indefinite integral. So I have to take the integral 4t plus 4 divided by t squared plus 2t plus 2 quantity squared dt. Well, what do we do? What can we do? What can we do? Well, we don't have very many tools available to us. If it's not one of our 8 integrals that we know by heart, we have to say we have to make it look like one of the 8. The first thing to look for is a substitution. So look for something on the inside, or look for a nice derivative, things of that nature. There's a function squared. This t squared plus 2t plus 2 looks a lot like something on the inside. That's a good candidate to try for a substitution. Now, a lot of these substitutions we can do in our mind. But because I have paper here, I'll use paper. So this is u equals t squared plus 2t plus 2. What would du be? 2t plus 2. And now it's like, oh, darn it. If it had been 4t plus 4, life would have been grand. But here's the thing. Constants are very easy to fix. Super easy. So, for instance, if you just doubled, twice du is 4t plus 4 dt. And then it's like, aha, we're good. We're in business here. So, what do we get? Well, we get the integral of 2 du over u squared. Or, because we're doing calculus, we write this as 2u to the negative 2 power. So, what is the antiderivative of 2u to the negative 2?
Negative 2/3 u to the negative third.
Well, it's negative 2, but the negative comes from, you add 1, so it'd be negative 1.
Oh, yeah.
So then you divide by 1. So it's negative 2 u to negative 1 plus c, or minus 2 over u plus c, or, because we want to get back in terms of t, minus 2 divided by t squared plus 2t plus 2 plus c. All right, so that's our velocity. We don't have enough information right now to figure out c, because the only information we're given is information about what happens with position. So we just have to accept that c is there for the time being. So now we move on and say, well, let's go to position, because that's something we know about. So position is the antiderivative of velocity. So that's the antiderivative of negative 2 over t squared plus 2t plus 2 plus c dt. So the c comes along for the ride. Even though we don't know what it is, it still keeps going. We can't use our same substitution. I mean, we can try it, but we can see what would happen. If I substitute u equals t squared plus 2t plus 2, I'm going to get stuck because there's no 2t plus 2 upstairs. So that's not going to work again. So I'm going to need a new idea. So I start sort of rummaging through my collection of integrals I can work with. I say, well, I can work with like u to the powers, but the problem is, I don't really have a u to a power. Like log u is like 1 over u, but I really don't have 1 over u. And then I keep thinking about, well, there's always this really cool function called arctangent. Now, arctangent has a t squared downstairs, or u squared, depending upon. It's like, well, wait a second, I have a square downstairs. Let me work with that. So let me write this in a better form, though. So thinking of arctangent, I'd really want to have a perfect square. So I don't want t squared plus 2t. I really just want something squared. So I say to myself, well, t squared plus 2t, what would I need to add to make it a nice square term? What would I need to do it to make it complete? One more. Because then this would become t plus 1 squared. But I still have 2, so that splits into plus 1 plus 1. So my plus c. So if you stare at this for a little bit, so that's negative 2. Then I have 1 over, and I'll write it this way, 1 plus t plus 1 squared plus c dt. Okay, and at this point, we can now pretty much integrate it. If you're not comfortable doing this in your head, I'll tell you what to do. You would say, hey, this t plus 1, set u equal t plus 1, and then du equals dt, and then you're off to go. So, what does this become? The answer is negative 2 arctangent of t plus 1. Then you have to integrate the c, so that's c times t, and then because you took an antiderivative, another constant enters into the fold, and that's d. So we have two constants to figure out, c and d. So let's start using information. We have information. We know at time 0 it's located at 0. What can that help us solve? It should help us solve for d, right? So if I put in 0 is where I'm at time 0, well, that's minus 2 arctangent of 1 plus 0 plus d. What is arctangent of 1? Pi fourths. Good. Oh, you guys are like picking up on arctangent. You're going to be like arctangent experts. You're going to go home to your family, sit around, roasting chestnuts over an open fire, whatever that means, and you'd be like, let's just talk about arctangent. It's so cool. Your little siblings or maybe your cousins are going to be like, arctangent, I wish I was in college. They don't give us cool functions like arctangent. So, negative 2 times pi fourths plus d equals 0, so we can conclude that d is pi over 2. All right, so now we have the following. Updating, our position looks like negative 2 arctangent t plus 1 plus some constant ct plus pi halves. Now let's figure out c. Now the other piece of information that we have is the following. The particle moves to a finite location as time goes to infinity. Let's think about what happens as time goes to infinity. If c were positive, what happens? Where do I end up at? I end up at infinity. Because pi halves stays pi halves. Arctangent is nice and bounded. It doesn't blow up. So if c were positive, I'd end up at infinity. What would happen if c were negative? I end up at negative infinity. But I don't end up at infinity. I don't end up at negative infinity, so what must be true about C? 0. C is 0. So C must be 0. So otherwise, you blow up. Because we know it doesn't blow up, yeah. Okay, so that's cool. So what we really now know is we now know C, and we know our position. So S of t is negative 2 arctangent t plus 1 plus pi halves. So we're ready to answer our questions A and B. So let's start with A. The velocity of the particle at time 0. So for velocity, I come into velocity function, but I can actually update because I now know that C is 0. So the velocity function was actually negative 2 t squared plus 2t plus 2. If I plug in 0, what does this become? Negative 1, because the t squared plus 2t vanish. So velocity at 0, negative 2 over 2, negative 1. So the other question is, what happens to S of t? Well, let's think about this. The pi halves is pi halves. What happens to arctangent as arctangent goes towards infinity? The input goes towards infinity. Arctangent approaches what value? Approaches pi halves. Has horizontal asymptotes, so pi halves towards plus infinity, negative pi halves towards negative infinity. So this goes to negative 2 times pi halves plus pi halves. So where do I go? Negative 2 times pi halves plus pi halves gives me position of negative pi halves. So that's where I'm heading off to as I head off towards infinity. And that's it. We're done. It's actually kind of remarkable that we can figure out these two answers, because it doesn't feel like we have quite enough information, but we do. It's the best part. You know, it's like, can we answer this? Yes, we can. All right. 4. On to number 5. Find the following integrals. So, 2 integrals. Part A is a definite integral. So when I have a definite integral, I want a number. Part B, indefinite integral. So I want a function. All right, well, let's think about how we can do this. So here, I'm looking at this. I say it's not one of my functions I know how to integrate. So I start thinking about things I can do to manipulate. Now, one of the things that we often do to obfuscate things, you're probably thinking, why do you obfuscate things? Well, because we love students having the chance to do algebra. This e to the 2t is another way to write the following. So whenever you see e to powers, you can say, should I really be rewriting it in a different way? In particular, you can write it as e to the t quantity squared. And if I write it this way, you say, hey, I see something. Both terms on the inside have an e to the t in common. Well, they both have e to the t in common. Pull it out. And in fact, not just pull it out, let's just pull it out and take the square root. So we'll do that. So we pull out that e to the t that they have in common and take the square root of that. That becomes e to the t over 2 square root 4 minus e to the t dt. And I was like, great, so we've now rewritten it in another integral that we don't know how to do. That's okay. We try stuff. And maybe we could say, well, maybe there's an idea here. Let's think about substitution. We should always have on our substitution hat. Now, we should always have on many hats, but substitution is one of the big ones. It's one of the ones we wear most often. If I'm thinking substitution, I say, I want to look for something that's either on the inside or that's a good, easy function to substitute, or something on the outside that has a nice antiderivative. Now, on the inside, I have 4 minus e to the t. The problem is the derivative of e to the t is e to the t, and I don't have that. Let's look on the outside. I have e to the t over 2. Does that have a nice antiderivative? Yes, essentially it's e to the t over 2 again. If I have e to any constant t, the antiderivative is essentially, now the word essentially means up to a constant, the same function. So let's actually try that substitution. U is e to the t over 2. What would du be? Well, it'd be e to the t over 2 dt, but there'd be something else. A half. Because you have to chain rule. But, using my fancy paper technology, I can move the half to the other side. All right. Well, this is fine. That can help me get rid of the e to the t over 2 and the dt. Can I do something nice with the e to the t? Well, what I can do is I can say, well, e to the t I can get by squaring. So e to the t is u squared. All right. Now, plug in our bounds. Plug in t equals 0. E to the 0 is 1. Log 4. Maybe we should do that one up by hand. E to the log 4 over 2. What's another way to write that? Yeah, well, yeah, it is 2. But do you see why it's 2? You can think of it in a couple ways. You can think of it as e to the log 4 to the 1/2. And e to the log of something is the something, so it's 4. So 4 to the 1/2. And pretty much every other way is equivalent to what we just talked about. So now it's like, okay, integral from 1 to 2, double of square root of 4 minus u squared. This at least feels simpler. Now, we don't know the antiderivative of the square root of 4 minus u squared. But we don't need to, because what is that shape? It's a circle of radius what? Radius 2. So, it's radius 2 going to 1. And I'm finding this area here. Well, the problem is, how do you actually find that area? Here's the idea. If this is 1, this length is 2, this is root 3 is the height, because it's a nice triangle. Turns out this is a nice angle. Do you know what that angle is? It's a 60-degree angle, but because we talk calculus here, we say pi over 3. So this angle here is pi over 3. And you're probably like, okay, congratulations, it's a pi over 3 angle. But why do I say that? Well, the reason I say that is think about my shape as a combination of two things. You have a wedge here, which includes the whole thing. Then you subtract out the triangle. And then what's left is that piece that we want. Now, to find the area of a wedge, you say, well, how much of the circle does it take? Well, if it's an angle of pi thirds, it's actually 1/6 of the circle. So the wedge would be 1/6 of the area of the circle, and the area of the circle is pi r squared. So that's the wedge. Subtract, what's the area of the triangle? Well, 1 is the base, root 3 is the height, so 1/2 base height. So now we put it all together. 4 over 6 is 2/3, so we end up with 2/3 pi minus square root of 3 over 2. And that's that one. That's part A. That gets us to part B. Woo! Part B. Part B. Okay. 1 over y plus square root of y. Now, just looking at this, is there anything that we can do? Is it on our list of 8? No. You might be like, oh, I bet you it's another arctangent. Well, we've already used arctangent like a couple of times on this one. Maybe we can't have everything be an arctangent. Well, we live the dream, someday maybe. But, all right, so let's think of things we can do. What are some things we can do? Think of ways to rewrite it.
You can do the y to the negative 1, then y to the negative 1 times e to the power of 1.
Well, you have to be careful here because addition is a finicky thing when it's downstairs. So we can't quite do that. We can't write it as 1 over y plus 1 over square root of y. It'd be good, but then we'd have to fire all the mathematicians because it'd be too easy.
Split up the fraction. 1 over y and then 1 over.
No. That's not going to work. It's not going to work. Again, we got to keep the mathematicians employed. We got to make sure things are complicated. Conjugate, well, that's an interesting idea, but I think that'd be a hard one for us to do in the amount of time we have. Can I suggest something? I'm just going to say it, because I like things. One of the things is say, well, why don't you factor out what they have in common? You're like, they don't have anything in common. Yeah, they have something in common. They're both powers of y. Let's pull out the smallest power of y. What's the smallest power of y? Yeah, 1/2. So it's square root of y times square root of y plus 1. Now at this point, it's not so obvious how that helps us. But now I say, well, now I have two pieces. And I go back to the substitution. When I'm thinking substitution, I think of one of two things. Either look for a piece that's on the inside that has a nice derivative, or a piece on the outside that has a nice antiderivative. And in this case, it doesn't matter which one you pick. We're going to end up heading the same way. So, is there a piece on the inside that has a nice derivative? What if I set u equals square root of y plus 1? Let's just see what happens. Now, the reason I suggest making this be your u is that plus 1 is going to be hard to work with. So that's the one you want to avoid. So set u equals square root of y plus 1. What would du be? Well, the plus 1 goes away. Half y to negative 1/2 dy. Again, I'll use my fancy paper technology, move the 2 across. So 2 du is 1 over square root of y dy. And hey, check it out, 1 over square root of y dy. So this becomes the integral 1 over u du, and then there's a factor of 2 coming from here. Do we know the antiderivative of 1 over u? Yes, in fact, it's on our list of 8. Explicitly, this one is special. It's not just u to any power. 1 over u is special. What does this become? Lateral log. And of course, because we want full points, don't forget the plus c. If you forget the plus c, we're going to come down and say, ah! Remember to, well, we may not, we won't hear that on the test. But we're going to be like, why? We keep telling them the plus c. And because we have an indefinite integral, you've got to get back to your original variable, so you've got to get back in terms of y. All right. So that's number 5, which leaves us with number 6. Now, number 6 is kind of an interesting problem. So we're given that g of x satisfies some information. G of 0 is 1, and the derivative of the integral from g of x up to x of t squared dt is 1. And the question is, let's determine g of x. So a priori, we don't really know what it is. It's probably something pretty nice, but you never know until you try it. Let's go ahead and start by taking this derivative. To take this derivative, what tool do we need? The fun tool. That's right. The very fundamental theorem of calculus. So particularly the first variation that allows us to take the derivative of a function to a function. Remember that says the derivative integral from g of x to h of x of f of t dt is f of h of x h prime of x minus f of g of x g prime of x. That's just a generic formula. I'll write it down so no one can say, you never taught us that. It's right there. All right. So applying it here. H is your x. Plug it into your t squared. That becomes x squared. And then times the derivative of x, which is 1, minus g of x gets plugged into t squared. So it's g of x squared times g prime of x. And that's equal to 1. So I'm just taking literally the derivative, set it equal to 1. Now we can't solve for any information yet because we know g of 0 equals 1. We don't know what g prime of 0 is. And we don't know what g of x is. But let's try to isolate g of x. So one thing is we can just sort of swap. So I can say that g of x quantity squared times g prime of x is equal to x squared minus 1. And now we sort of put on our thinking caps and say, does g of x squared g prime of x, does it remind us of anything that we've kind of seen before? Kind of reminds us of chain rule, right? Chain rule of what? Well, if it was a chain rule of x squared, if we're taking the derivative, it would be 2 g of x to the 1. We want g of x squared, so maybe not x squared. What's the next thing to try? X cubed, right? Because if you took the derivative of g of x cubed, that would work. So let's put a 3 here. And we can also put a 3 here. As long as I do it to both sides, I'm okay. So this really, on the left-hand side, it's the derivative of g of x cubed. That's equal to 3x squared minus 3. So now I can take the antiderivatives. Antiderivative of g of x cubed is g of x cubed. Sorry, antiderivative of the derivative of g of x cubed is g of x cubed. Over here, antiderivative, well, antiderivative of 3x squared, x cubed, minus 3 becomes minus 3x, and then we have plus c. So we're not done because we don't know c, but how do we find c? Plug in g of 0. So 1 is equal to g of 0 cubed is equal to 0 minus 0 plus c. So what does that say about c? C equals 1. So we now have that g of x cubed is x cubed minus 3x plus 1. So g of x, to get that, take the cubed root. So g of x is the cubed root of x cubed minus 3x plus 1. You know, in retrospect, we probably could have guessed that before we even started. No! We had to do the math! But we have the tools to do it. That's the great thing. Now, let me give you one last word of advice. The practice exams are great tools. Don't just study one practice exam, study both practice exams. If you study both practice exams, you're going to do pretty well. If you study one, you'll do okay. If you study none, you'll do eh. Don't limit yourself only to the practice exams, but if you're going to do just the bare minimum, do at least those.